Okay? So, we are experts by now. At the moment, we are experts doing some theoretical issues regarding dynamics of systems and regarding the vibrations of systems. But we're going to have some expertise using a computer program. Okay? If that doesn't motivate you, it's going to motivate you is that you need to pass this module eventually. And doing a project, because you are going to do the project, right? Next semester, next year, you're going to use this software. Okay? That being said, before actually going into the subject, let me just have a look back to what we did yesterday. How do we call this element here, which is defined as the logarithm of these two things? What's the name of that thing? It's there, the logarithmic decrement. So that means that the logarithm of this ratio is the same as the logarithm of this ratio, the same as anything. This could be arbitrary, x1 or x2 or x10 or x11, right? This is arbitrary. And that's a constant. You take the logarithm, it's a constant because you can see here, this is a constant, this is a constant, and this is the damped period. How do you calculate the damped period? This is just 2 pi over square root 1 minus this value squared omega n. Right? If this happened to be quite small, for example, this is lower than 0.1, right? This expression is very, very close to 1. So therefore, we can end up with this very simplistic form of the logarithm decrement. I believe this is well understood, isn't it? Right? In order to find this logarithm decrement, you just multiply 2 pi times this factor that you can calculate, and that's it. But the problem is that you don't do it in that way. What you actually do is perform an experiment in a system and get this curve. For example, you hit the system, you put an accelerometer here, you move this, and you record the data. For example, this starts vibrating, doesn't it? It vibrates, you put an accelerometer, you record the data, and then you know information about the amplitude of each of these points. Take the ratio between two of them, take the natural logarithm, and then you get the logarithm decrement, divide by 2 pi, and you get this value, right? That being something quite difficult to measure with other approaches, but you have to do an experimental dynamic approach like this one. You get the response, you divide that logarithm decrement by 2 pi, and you get this value, right? Easy peasy, isn't it? However, the data here might be good, the data here might not be that good. It might be probably better to estimate the data from some further point. So, for example, if you take x1 over x2, this is the logarithm. If you take the logarithm decrement of this thing, and then you get that value. x2 over x3, x3 over x4, x4 over x5. This is equal to what? x1 over x5, right? For example, if I have data here, and I eventually have some information here to x5, there might be a way to calculate the logarithm decrement with this information. How do we do that? This right here was given by this value, what else? Remember? Omega n, 2 pi, omega t. Is that right? And this quantity is the same for all of them. Right? So therefore this is going to be equals to e this 2y only the d to the power of, in this case, 4. 1, 2, 3, 4, right? To the power of 4. Take the natural logarithm of this thing over this thing, and then you get 4 times e this value. Is that right? Because this is eventually multiplying this thing, right? I just happen to put this in parentheses because what I could do is that this is 1 over 4 x1 xy equals this d. And what was the name of this thing? This is the logarithm decrement, isn't it? That's right. Oh, sorry. Correct. That's missing. Okay? So this is the general expression. If you want to have a logarithm decrement after similar periods, it's the very same formula, but you divide by the number of periods. Minus 1. Or by the number of periods, but this is plus 1. So a general form of this thing is this equation. M is the number of periods, in that case was 4, right? And here is 4 plus 1, 5. x1 over x5. So this is easy, isn't it? And the same argument. This is equivalent to this parameter times 2 pi, when this is lower than 0.1. Okay? So this works, since you have plenty of data, you might test for several points. And then this has to be a constant, but in experimental data, you don't have actually a constant, you have to average that out. Is that clear, guys? Perfect. Just for your information. That being said, let's start our lecture, today's lecture. In order to solve an equation, a differential equation, like ODE, that stands for ordinary differential equation, or EDE for Spanish, and you guys are experts at this, do it by hand, right? You can use a method that's called the Rondt-Kuhn method. Those were German guys who developed this method in order to find the approximate solution of an equation of motion. For the equation of motion that we have dealt with in these lectures, we do have an analytical expression, don't we? Right, this sinusoidal form, this exponential form, we do have analytical solutions to that. But for a general equation of motion, might be linear, might be non-linear, might be done, might be not done, might be forced, might not be forced, you use this approach to find an approximation. If you eventually take a module on numerical methods for engineering, you will deal with this method. Why do we need to deal with this if the software MATLAB has already implemented this in one of these softwares? That's called the ODE45. ODE45, ODE stands for Ordinary Differential Equation. 45 is one of the softwares, there are plenty of softwares that MATLAB has. But this is for non-stiff differential equation. That means that those differential equations that are going to be solved with this do have a solution, can be solved with a numerical approach. And this is a numerical approach. We are not going to give a lecture on what this method is, because you will find out once you go to the books or you take the module on numerical methods. You will deal with this quite a lot. We are not going to do that. We are going to use right away the solver of Matlab for these differential equations. Right? The good news, you are not going to develop the code. I'm going to provide you the code. If you go to the virtual room, virtual classroom, as we call it, Moodle, there is already a folder that says ODE45. Have you checked? Right? Open the folder. Inside there are two files, two Matlab files. We're going to explain what's the meaning of them. But before that, let me give you an example of how does this work. You specify the solution for t and y. T is time, y is displacement. Okay? ODE, and then you set the function that you're going to solve. The function, you define the time vector. Right? You are going to have the solution in a time vector. And you are going to specify a boundary condition. For example, this 1, 0. Another form to do that, with the same thing, and put some option. This option is a set of parameters that are going to improve the performance of the solver. Or you might have here some other solutions in a particular point, a specified point. I'm not going to deal with that. The solution of the system is just ODE45, whatever thing you have inside. For example, we want to find the solution for this equation, y dot equals 2t. This y dot is dy over dt. Is that right? And this is equals to 2 times t. We can find an analytical solution for this. Y equals what?
2 squared. T squared.
T squared. Is that right? So this is something that we can do because we know the solution. An approximation is using this code. You go here and define the time span. Time span is the numbers between 0 and 5 included in the steps of 1. Y0 is the initial condition. When t equals 0, y equals 0. You go to here. And the solution, that form is, we're going to have a solution for the time, solution for y, and this is the way to specify. This is the function. You can put this in Matlab, and you are going to have a solution for y, which is the same thing as you have here. But this is the real solution. Here you are going to have an approximation to this. And this approximation is going to be very good. Right? The more time it takes to perform the calculation, the better the approximation is going to be. Okay? There's not much that we can do here. This is the code that you need to modify. For example, you want the solution from 0 up to 10 seconds. 0, 10. You want different steps. For example, you have a linear space between 0 and 10, and you specify the step. You specify the initial equation, the initial condition. This could be 0, could be another constant, another value. Okay? Is this useful for us or not? Not quite. Because as you can see, this solver is designed to solve ordinary differential equation of the first order. And we are screwed because we have equations of motion up to the second order. Is that right? However, the guy who designed this thing was an engineer and said, it doesn't matter. We can convert second order equation of motion into a first order equation of motion. And then use the stem. So we need to do a trick in order to redefine this function. How do we do that? If we have this equation plus cx dot plus x equals 0, let me just give another name for them. Let me just put this 1, 1, 1. What's the reason for that? Because this is for 1 degree of freedom. We have several degrees of freedom. We will have several variables of x, x1, x2, x3, and so on. Right, let's just put this there. So, we are going to say the following. This variable, y1, is going to be equals to x dot 1. y1 dot is going to be equal to x double dot 1. Right? If you understand what I'm doing here, you are not going to have any trouble reading the code. What is y? Choose a new variable and define it. Okay? The solution for my system is going to be x. It's going to be a vector x1, y1. This is the solution. And what is x1? This is the displacement, isn't it? The displacement that we got here. This is a vector. This is how you call this value. And this thing, this 2, is how you call this value. This is the syntaxes that you use in MATLAB. Okay? This is x, x1 is this thing, x2 is this thing. But what is the meaning of this? This is displacement. Am I right? What is the meaning of this thing? What is this? y1. This is not displacement. What is this thing? This is velocity. Right here. This is velocity. But in this form, this looks like displacement. But it's not. It is velocity. So this is a vector of displacement. This looks like, but it's not. Now, let's define the derivative of x with respect to t. We're going to have x1 dot, y1 dot. Okay. What is this? x1 dot. This is velocity, right? It's like the same value that we have here, isn't it? So this is x2. Is that right? And this thing here, what is this? This is the acceleration of x1. You got it here. And the acceleration of x1 equals to what? This. Right? Equals to what? It's 1 over m that multiplies minus k x1 minus c x2. Do you agree, guys? Where does this thing come from? Right here. This is the equation of motion. We're just going to solve for x double dot. So we put this on the other side with the minus sign, and this goes to the point. Right? But we can work out this further. What is this x1 in here? It's going to be this thing, isn't it? And what is this x2 from this? x2 is, I'm sorry, this is x1 dot, right? What is this? x1 dot is this one. Is that right? So x2. And that's it. We are going to define a first order equation of motion, because this is just the first derivative, and then we're going to have the solution for the first order. The first solution is going to be displacement, and the other thing is going to be velocity. So the problem is simplified, and furthermore, we don't have just the solution for displacement, we have both the solution for displacement and velocity for the very same system. Everything that I have done here is provided for you in this code. Let me explain. This is a function that we have created. In one of those files, you will have this function, and this is the name of the function. Right? This is a function of what? A function of time, a function of x, the displacement. This is the constant k, this is c, and this is m. Right? So wherever is going to be described here is going to be a function of everything inside here. Let me explain. X is going to be the solution for this. The solution for this is just going to be x and x dot. Right? The first item here, x1, you know, is displacement. The second item, x2, is velocity. Right? We're going to define now the first derivatives because this is what the function is going to do. So this dx dt, the beginning is going to be 0 size x. What's the meaning of this? You are going to have an empty. That's going to be the solution, 0, 0. And we are going to fill up this with information after we compute. Now that this is defined, we're going to give a value for this thing. The first thing is going to be x2. What is x2? x2, what is this? X dot, right? And the other thing is going to be here. It's just going to be all of this. This is x dot dot. What we did in the blackboard already. And that's it. Now, this is a function of our first order equation. The solution is going to be solution in displacement and velocity. I do apologize, this is not supposed to be smart.
Can you explain why you?
For some reason the code is modified, the code doesn't have that. Once this is done, we go to Matlab, and if you want, you define the options. Well, I have defined the options for you. There's no need to understand what's the meaning of this. This is a relative tolerance. We put the lowest possible stats that the analysis is going to be eventually statistic. This allows a statistic we are not going to use anyway. And this is the step. This value here has something to deal with the approach. In the approach, if you have a step which is very large, you are going to have a very rough approximation. If the step is very, very fine, you are going to have a finer approximation. But the problem is that if this value becomes very small, we are going to have the best solution that's going to take more time for computation. If this value is very large, the approximation is not going to be that good, but the solution is going to be pretty quick. Right? What I'm doing here is just explaining what is the meaning of this. And here is the code. Here, we are calling the function that we just defined previously. Right? ODE45, we call the function. Time is a vector of time that has to be defined. This x here gives you the initial values or the boundary condition. x0, velocity 0. Right? You call the options that you just defined there, and you put the corresponding value of k, the corresponding value of c, the corresponding value of m. click play, and you get the solution right away. Okay? If you have questions or have questions, let me just explain you how it works.
Because you use 0 size x. What is it?
Here,
Yes.
because you're going to define a vector for this, but that doesn't exist. So you just define this, and now this exists. Doesn't matter whether this is zeros, it might be 1, 1, doesn't matter, but you are just defining it. Now it exists. Once this exists, you are going to put information. If you don't want this, you could directly say the x dt equals, in establish x2, comma, 1 over m minus x x1 minus c x2. I did this just to organize, to make this more simplistic. Or you just define this thing, right? Both are good. It's a good question. And remember, this doesn't have to exist. There's one reason why it's under explain. Okay. Now, let's work out. So this is what you will find in Moodle. You will have this, which is the function that we have just defined. Look, this is correct now. Right? Only these 3 lines, actually it could be just 1 line. Right? Is this function, but I did this in steps to explain what's the meaning. You come here and you define one value of k, one value of c, one value of m, and you can calculate this omega n. What's the meaning of omega n? It's the natural frequency, right? It's the square root of k over m. This is the critical damping, to the square root of kn, right? And this z here is the damping ratio. The damping ratio is given by c over the critical. This is going to tell you whether the system is oscillating, the system is critically damped or overdamped, right? Is this clear, guys? Everything here is clear. Yes. Right, hopefully. Now, I just put here display that the damping ratio is, once you calculate the damping ratio, the natural frequency is, once you calculate the natural frequency. And now, if this value is lower than 1, there is another property of the system that exists, which is this, the damped frequency. How do you calculate? The square root of 1 minus z squared times omega n. Right? If this value is larger than 1, this doesn't exist. If that value is equal to 1, it doesn't exist either. Right? Everything from here to the top is just defining the problem. Now, I'm putting here some discrete input data in order to create the time vector. The time vector is going to be a vector that goes between 0 to a maximum time that you can specify here. And how many values does the vector have? I put 100, for instance. Right? So here, time is a vector of 100 elements that goes between 0 to t maximum. The maximum, I just put 50, just for an example. And then I define critical conditions, the initial conditions. For instance, x0, the initial displacement, equals 1, v0, the initial velocity, equals 0. You can play with it, you can do whatever you want. Okay? What else do we have here? Here is the code. What I'm doing is just calling the code. This is the function that we define, and we are putting here the corresponding values for initial condition. We have this, right? I put the maximum step. Once you run the code, this is going to give you a solution for t, which is a new vector of time, which luckily is the same as the previous one that we defined, and x, which is going to be the solution of the system. All right? The solution of the system has two parts. The first is displacement, whereas the second is velocity. So by solving this equation, you are going to have both of them, velocity and the displacement. Right? There's no need to differentiate the displacement to get the velocity. You got that right away. And finally, you can plot this. How do you plot? Plot time, and what I'm plotting here is displacement. If I put this 2, it's going to be velocity. And let's see what we have here. Play around. And there you go. This is an approximated method. Happened to have performed 185 steps, but one of those steps failed because this is probably, this value is probably quite large. But one failed attempt in 185 and actually 1,000 of function evaluation gives quite a good solution, doesn't it? And look at this. For some reason, what do you think of this curve? What is the response of the system? Underdamped. It's oscillating, right? You have the initial displacement and then the curve reduces. Do you like it? Does it look nice? It doesn't. Because you can see these corners are quite awful. How do you solve them? You go here and change the number of data. Let's put 1,000 data points there. And let's see what we get. This is the previous one. For some reason, looks better, doesn't it? More rounded. Okay. Let's change the data. Let's increase the damping. What occurs if we increase the damping? For example, let's put this equals to 1. Run the code. This is the previous. And this is the new one. This is more damped, isn't it? All right? And you could also put a large value, let's say 3. Run the code. What do you get? This is heavily damped. All right? So, what is the beauty of this? You don't need to remember the equation, the solution for the equation first. Second, this gives you right away the solution for an underdamped, overdamped, critically damped system. And the third part, the most important, this is not restricted for linear equations of motion. We're going to see why. If you liked it, this is your first task for next year. Propose a single degree of freedom system. You can go to the book and find it. You can actually do anything that we have done already in lectures. Up to you. Find an interesting one. Find the corresponding equation of motion. And with this equation of motion, determine the parameters. Equivalent stiffness, equivalent damping, the equivalent mass. Right? What's the easiest thing to do? Go to the book and find a solved problem. Go to your notes and copy one of the problems that we have already solved. Go to one of the things that you have done as homework, right? If you want to find a new problem, or to choose anything that you have done already. With this, put the information into the code that is provided for you and find the code. Try to change this value in order to make the system underdamped and overdamped. How long this is going to take? 2 minutes. Right? So don't panic that I'm going to take your holidays. No, this takes 2 minutes. Go to the code, put the data, play, and you go to the code. Okay? Everything clear, guys?
Yes.
Perfect. Now, here is the beautiful part of this. This code is not restricted for linear equations of motion. You can do anything you want, including non-linear. For instance, you remember the equation of motion of this thing. It was theta double dot plus g over L, theta equals 0. Remember?
Yep.
Right? But this is not the true one. The actual one. Sine theta equals 0. This is the actual one. You guys remember? But we said that for a small oscillation, this becomes theta. And this becomes a linear equation of motion. As I mentioned that there's no restriction for you to use the code, you can put this. Theta double dot equals minus g over L sine theta. Right? And this looks like K, doesn't it? Right? So, let's work this out. Here we have a system, and for this equation, let's modify something. So, what is the mass? The mass looks like 1 in that equation, doesn't it? Right, so let's put 1. It is 1. What is the value of C? 0. Let's put 0. What is the value of K? G over L. Right, so let's say that this thing has 1 meter length. G over L is going to be how much? 9.8. Right? This is the first modification. The second modification, go here and change this definition. So now we don't have x1 or theta. We don't have this. What do we have instead of this? Sine theta. This is going to be sine. We can modify this. Set it. We now run the experiment. Now this initial displacement is going to be 1 gradient displacement, right? Let's play it, and let's see what we get. Let's reduce this. Let's put just 10 seconds. And look at this. This is the solution. Do you see something new? No, it looks like the sinusoidal, right? It looks like that because one region is quite small. Let's put a bigger one. Let's put 2. Let's put 3. 3 regions displacement. How big is 3 regions? How much is this in regions? 180 degrees in regions. How much? Pi. Pi equals 3.4. Right? So 3 is quite close to this point, right? This is a very large volume. So let's see what we get. This was the previous, and there we go. Does this look like a sinusoidal? It is not a sinusoidal any longer. Let me close this thing. And let me put this. Very, very close to the top. This is the solution. This is not a sinusoidal. It is impossible to find an analytical solution for a pendulum. But this code gives you a good approximation, which is that one. What did we do? Just modify the code. Is that clear, guys? Do you have a question? No questions? Well, in that case, I do have a question for you. Remember, if you don't ask, I do ask. Here we have 2 nonlinear equations of motion. The first one is called the van der Waals oscillator. This comes from electronics, from electrical engineering. So this guy happened to develop this thing way before we had computers in the beginning of last century. Can you imagine solving this problem previously? It's difficult. Now, what is this? This is the acceleration. What is the constant of the acceleration or the mass? It's 1 here, right? This is velocity. And the coefficient of the velocity, what is this? It's not a constant anymore. This mu isn't it a constant, but this is displacement. Okay. And the displacement has a 1, has a k constant, doesn't it? Now, this is a Duffy resonator. This is a better approximation of a real spring. Because a real spring, once you stretch it and you close to the limit, you change the value of k. It becomes very, very large. So this is a constant, which is the damping, right? This is a constant, which looks like a stiffness. And this beta is a constant, but now you have x to the power of 3. So this is a nonlinear oscillator. Both of them are nonlinear. And my question was, could you use the software to plot the response of either of them if you define some values? Can you do that? You have already the function. The function was defined for linear problems. Where was the thing? Here is the thing that has to be modified. This thing here. So for x equals for everything and put it here. Right. If you do that, you get the solution. So, can you do that? Actually, the second one is easier. Both of them are very, very easy. In order to prove, select either of them. Choose the van der Waals or the Duffy equation, put parameters and plot it. If the previous problem took you 2 minutes, this is going to take you 30 seconds. Right? It's extremely easy. Just modify this line. This line of code. This has to be modified. Okay? Modify this thing and put values Yeah. Put values here for initial displacement or initial velocity. Change the values here accordingly, the ones that you choose. And if you don't like the response up to 10 seconds, change it. It's up to you. Just for you to play with the code. You don't need to modify anything. Just go to the function and modify the function accordingly to this. To here, double dot equals minus x plus 1 minus x squared. X here dot equals minus delta dot minus alpha x minus beta x cubed.
What's the difference between the first one and the second?
The first one has the nonlinearity in the velocity. The second one has the nonlinearity in the displacement. That's the difference. This is useful for mechanics. This is useful for electronics. So which one are you going to choose? Mechanical one. You're mechanical engineers, aren't you?
What was the meaning of the constant?
Of this constant. This constant.
Yes, the
Equivalent to damping, stiffness, and this is the cubic stiffness. That's the meaning. The value for this is an equivalent to damping.
Good.
Is that clear, guys? Not clear. What's not clear? So, if you go to your desktop, open your computer, you have multiple computers, right? You have access to the code. Just find this thing and put this information in the previous code. What was x? x1, right? What was here? This is x1 squared. What is this? This was x2, right? What is this? This is x2, this is x1, and this is x1 cubic. It's already solved. Now it's going to take you 15 seconds. You just need to write down this previously. Okay. Previous equation was defined for M, C, K. I have to make a link to them. They will see.
In this equation, the value of m is 1.
Yeah, it looks like 1. This is 1, K here is 1. Right? Finally equivalent to this. In this case, M is 1, this is C, this is K. Right? This is a new value that you can just choose here. Find any value. If you choose 0, you will get 0. Okay, guys, so thank you very much for coming today. Hopefully you enjoyed this. If you didn't, you can have one at home when you do the homework. Please review your homeworks. Please review anything that we have done in lectures, because this is going to be in the test. Right? Actually, I mentioned 2 of the problems that are going to be in the test. But they are not going to be exactly the same. Try and modify them. Try to put new values. Try to ask yourself, what else can I do with this problem? And then you will get 10 out of 10 next test. Right? Okay, guys. Thank you very much for coming today. See